All right, welcome to the first video I'm going to be doing on Beyond the Formula Tutoring. So actually, I did this on a Zoom recording to I was teaching a group of students, but unfortunately, I forgot to record at the very start. So I'm just going to be going over the first couple minutes, and then I'll transition to the Zoom recording where I taught the larger majority of it, and then at the end, it'll go back to a recording like this because the Zoom meeting ended and I forgot to click record again. Okay, so let's look at our first topic here, concavity. So concavity is basically just focusing on rate of change. So you don't have to worry about whether the graph itself is increasing or decreasing, but you do have to focus on whether the rate of change is increasing or decreasing. So here, this graph is concave up. So what does that mean? So concave up means that the whole graph, the rate of change is increasing. So I'm going to show you guys what that means. So here, let's look at this point right here. All right. I hope you guys can see my cursor. Let me, if I can make it bigger. I don't think so. Okay. So this point right here, let's estimate the rate of change at this point. Maybe it's like just a rough estimate. I'm gonna say like maybe it's like -1 along this point. -1. And let's draw a line to signify, sorry, that at this point it's -1. And then let's look like at this point, it's the vertex. So and we're gonna get into more about the vertex and that later. So over here at this point, right here, the rate of change is gonna be 0. So first here it was like -1 around that, and here it's 0. And then let's take a look at this point right here. Let's draw a line. Okay, that looks to me like about 1, somewhere in that range. So it goes from -1 to 0 to 1. You can see that it's increasing. So basically, as the x values increase without bound, the y values are increasing. No, the rate of change of the y values are increasing. So and then now let's look at concave down. So it's the same idea, right? Here, the rate of change, it's around 1. And then there's a line to oh my God, I can't talk. That. And then here it's 0, and here it's going to be -1. So as you can see, first the graph seems to be increasing, and then it slows down and then it starts decreasing. So now let's look at this significance of these highlights. So the red highlight, yellow highlight, yellow highlight, red highlight. So let's look at this part first, right here. So in this part, the graph is concave up, so the rate of change is increasing, but you can see that the graph itself is decreasing. So as x values are increasing, the y values are decreasing. So on this portion of the graph. So that tells us that, and how we put that into words is uh the graph is concave up, and therefore the rate of change is increasing as the y values are decreasing. And then this portion right here, the rate of change is increasing while the y values are increasing. So it's going up, and then it's going up at a faster rate of change. So it's getting more steep. Concave down, it's the same concept, except here the graph is increasing as the rate of change is decreasing. So it's going like it's decreasing. You can see there, maybe it's like a slope of -2 here, and then here it's negative, it's, no, sorry, +2 here, and then here it's 1, and then 0, but still the y values are increasing. And then on this point, the y values are decreasing as the x values are increasing. So the graph is decreasing on this red portion, and the rate of change is uh decreasing since the graph is concave down. And there's multiple ways you can remember the concave up and concave down. So for concave up, you can think like up increasing, rate of change is increasing, concave up. And also up, it's kind of like a smiley face right here. So that's being positive, so it's up. And then while down is the rate of change is decreasing, so down and decreasing, and then like I'm feeling kind of down, so it's like a frown face, so it's a frown over here. So that's a couple ways you can remember it. And then here, so let's think about writing where this graph is increasing, right? I mean, where the rate of change of this graph, where is this graph, the concave down graph? Let's look at this graph right here. Where is it increasing at a decreasing rate of change? So clearly, it seems this arrow indicates that it's decreasing all the way since x is negative infinity. And whenever we're working with infinity, whether it's negative infinity or positive infinity, you're always going to put a parentheses because that indicates that infinity is not included. And since it can't be included, and then it increases until zero. And at zero, since that's our vertex, that's also not going to be included because the rate of change, the graph isn't increasing or decreasing here. So if I asked you, where is this graph increasing at a decreasing rate of change, you would say negative infinity to zero, both non-inclusive with parentheses. Now, let's look at points of inflection. And this is about where it's going to cut to the next zoom. So I'm just going to go over the start of it real quick. So concave down, concave up. So this graph is concave down, concave up because, okay, here let's like estimate the rate of change to be around 1, right? And here the rate of change is around 0. We're estimating again. And here it's -1. So this looks like a concave down graph, right? Here, on the other hand, if we scroll down a little, looks to be concave up because here maybe it's like -1. And then here it's like 0. And then finally here it's going back up to 1. So it looks like the graph is split between concave down and concave up, but it's still one graph. And now I'll go over and cut it to the next clip. Okay, so back to this part, right? So it's concave down over here, and then because here the rate of change it's around -1, here it's around 0, it's around -1. And then here, after this point, the rate of change starts to increase, which means the graph on this side is concave up. So that changes at a specific point. Any given graph that changes between concave up and concave down, it changes between the two at a specific point, and that point is called the point of inflection. So here on this graph, we'll label our point of inflection as -1, -1. When when you're being tested on points of inflection, they'll never ask you to find the exact coordinate where it's changing because it's impossible to determine without like uh calculators and advanced calculus, right? But it's simple to just see that at this point, like around this point, the point of inflection, this is the point of inflection, right? And then if I, again, the point of inflection, similar to the vertex, if I asked you where is this graph concave down, you would say it's concave down from negative infinity to -1 with a parentheses, not a bracket, because the parentheses indicates that -1 is not part of where the graph is concave down. Now, if I ask concave up, sorry, it's the same idea that -1 is not part of it. So there's a parentheses and it goes to infinity. Any questions on that? Okay. I'm gonna give you guys a problem now. Okay. So you guys can see this graph. Ignore the left portion now. So what portion of this graph is concave up and concave down? And you guys can send it in the chat directly to me so that everybody has a chance to answer it. And then you can also answer the second question, which is what are the 2 points of inflection on this graph? Pranav, that's not the right answer, but wait, were you trying to answer the first question or the second question with that, by the way?
The first one.
Okay, the first one. Yeah. Um, so yeah, try one more time. I'll explain it after too. You weren't here at the start of the meeting, so it makes sense. I'll give you guys like 2 more minutes and then I'll go ahead and explain the answer. All right, I'm gonna go ahead and explain the answers now. Arvin, good job, you got it right, and uh AM, you also got it right. It's the only thing one thing for your answer, AM, is that B and D aren't the points of inflection. Those would be like the places where the rate of change is zero, which like are like vertexes in like a quadratic, for example. But the point of inflection is a little different. So I'll explain it now. First of all, it asks us what portion of this graph is concave up and concave down. So if we look from negative infinity here, okay, it looks like the rate of change is decreasing, right? Because first we're going up and then we start going down, which means the rate of change is decreasing here, and therefore the graph is concave down at the start from negative infinity. So negative infinity to A to B, and B to C. So negative infinity to C, the rate of change is decreasing. So it's concave down. And then after C, the rate of change starts increasing. So C to D, it's increasing, and then D to E, it's increasing again. And then at E again, it starts decreasing. So from this, I want all of you guys, whoever like to say, what are the 2 points of inflection now that you know where the graph is concave down and concave up? And remember that the point of inflection is just when the graph changes from being either concave down to concave up or concave up to concave down. And by the way, Pranav, your second answer was correct in the chat. Yeah, that's right, Am. C and E. So do you all understand why it's C and E? So if we're looking here, the rate of change is decreasing. And at this point, C, it changes from concave down, where the rate of change is decreasing, to concave up, where the rate of change is increasing. The point of inflection is where it changes, the rate of change stops decreasing and starts increasing, or the rate of change stops increasing and stops decreasing. So in C, the rate of change is decreasing, and then after C, it starts increasing. And in E, the rate of change is increasing before E and then decreasing after E. So therefore, those are the 2 points of inflection. Now, here's a little more challenging question. How many points of inflection are there on this graph? Not quite, Arvin, but think about how much times it changes between being concave up and concave down. Yeah, Danya, Pranav, and AM, you guys got it right. There's 3 points of inflection. So let's look at the graph here, right? So from here, it looks like the graph is increasing, increasing, increasing. So the rate of change is decreasing here, right? Because here, look, it starts decreasing, decreasing, decreasing. And then around here, like somewhere around, not an exact point, but there, let's say that it stops decreasing and the rate of change starts increasing because now the graph stops decreasing and it goes up, it's going up, it's going up. And then somewhere here, let's say like around there, the graph, it isn't increasing anymore. The rate of change isn't increasing anymore, and the rate of change is decreasing. So now the rate of change is decreasing, it's going down. And now just think about it. If the rate of change kept on decreasing, then this line, it would just go all the way down. It would just go to infinity, right? But it's not doing that. So the rate of change is decreasing, and then somewhere around this area, the rate of change starts increasing. So it goes from decreasing to increasing, and therefore there's 3 points of inflection. Okay, now let's go to the next topic. So again, a lot on your screen. Don't try to focus on all of it at once. I'll explain it now. Okay, so first, let's look at this little thing right here. So the average rate of change over an interval. So this topic covers rates of change, right? And a rate of change is just basically the slope. So it's just a fancier way of saying slope, right? So and to find the rate of change, here's how we do it. So let's take 2 points, A, comma, B. So these points are going to be like the x coordinates. So for example, uh, from like -1 to 1, right? And then equals f of B minus f of A over B minus A. And this might look a little complicated, but it's really not. Once you guys see an example, I'm sure you guys will understand. So f of B just means the graph we're looking at, which is f, and then at the x value b, what's the y value, right? So minus where the y value is when the point is a, and then just b minus a. Now that might confuse you guys, but let's look at the example here, and then you guys will be fine. All right, so point A is at -3, comma -1. Point B is at 1, comma 2. Find the average rate of change between points A and B. So we'll all work on this problem together. So y'all can work on it too. And if you don't understand, then I'll explain it. Actually, just watch me explain this one first, and then you guys can try the next problem. So -3, comma -1, point B is at 1, comma 2. So A, B. Okay, this just looks like a normal line, right? Like a linear line. So basically, we're just finding a slope. So -3, comma 1. So where do we get these numbers? So first, the point is at -3, comma -1. Okay, so the x value of that point is -3, which, okay. So this is x value of point A, and then here is the x value of point B, because point B is at 1, comma 2, which is the x value is 1. Okay, now f of 1, now we're just plugging in our formula, right? A, B, so our A value is -3 and our B value is 1. So f of 1 minus f of -3 over 1 minus -3. And then we have okay, so what is f of 1 and what is f of -3? Okay, so f of 1 is just, we look at this graph and we're trying to find what is the y value when the x value is 1, right? The x value is 1 over here, and the y value is 2. So f of 1 is the same as 2. And then we look at the y value when the x value is -3. So the x value is -3 here, and it says, excuse me, that the y value is -1. So we do 2 minus negative 1 divided by, and then we get 4 because 1 minus negative 3 is the same as 1 plus 3, which is 4. And then if we just do the addition here, 2 minus negative 1, 2 plus 1 is 3 over 4. And yeah, I saw someone say in the chat that's the correct answer. It's 3 over 4. So you can write it down now. 3 over 4. Okay. Now, let's look at this. So before we were working with just a normal slope. Now we're working with a quadratic. So, or yeah, a quadratic. Not the default quadratic, but a similar one. And then, okay, let's look over here. Point A is at negative 2 comma 3, and point B is at 1 comma 1. What is the average rate of change between point A and point B? So let's just plug in our formula here. So the x value of point A is negative 2, and the y value of point A is 1. I mean, not, sorry. The x value of point A is negative 2, and the x value of point B is 1. Okay, now let's look. We're just plugging in our formula here, right? The second number, which is 1, a function of 1, f of 1, minus f of negative 2, divided by 1 minus negative 2. Now, what's f of 1? So f of 1 is just going to be 1 because when x equals 1, which is over here, it says point B is at 1 comma 1, which means point B is at when x equals 1, y also equals 1. So that's why we have 1 over here. And then for f of negative 2, we have the y value is 3 because point A is at 3 when x equals negative 2. So 1 minus negative 3 divided by 3 because we get the 3 on the bottom because 1 minus negative 2 is 3. And then we just do the uh, subtraction and it's negative 2 divided by 3. So negative 2 over 3 is our answer. All right, any questions on that problem right there or the problem we worked with before? All right, nice. And also the Zoom meeting like just gave me a warning that the meeting might like cut out soon because there's a limit of 40 minutes. So just when it does, just be prepared to join back. I'm gonna continue after that. So yeah, I'll see what I can do about that in the future, but for now it's just what it is. Okay. Yeah. All right. Next, let's look at this topic. No, this question, sorry. So point A is at negative 2 comma 1 and point B is at 4 comma 2. What's the average rate of change between point A and point B? So you guys can just put in the chat when you get the answer. Try to text me directly. Like there should be an option so that you guys so everybody else can get a chance to work on it as well if you finish quicker. Yeah, that's correct, AM. Yeah, that's correct, Anya. And uh not quite Pranav. You're almost there though. And yeah, for the the normal just Pranav, yeah, correct. And Pranav H, not quite. Try it one more time. Yeah, I'll explain in like a minute. All right. I'm gonna give you guys like 10 more seconds. All right. I'll explain the question now. Okay, so point A is at -2 comma 1 and point B is at 4 comma 2. What is the average rate of change between point A and point B? Okay, so let's just set up our equation here, right? So x value -2, comma, and then the x value for point B is 4. So this is the domain of the one we're trying to find. And then, oh, ran out of space there. I'll just go down below. Okay. Here four. Okay, then we just plug in our formula, right? So the y value when x equals 4, which is 2, minus the y value when x equals -2, which is 1, divided by the b value, which is 4, minus -2, which then we just do the subtraction, equals 1/6, which is our final answer. Okay. Now we'll go to our next topic, instantaneous rate of change. So this is something that it'll give you earlier up here. We were like, when I was explaining concavity all the way over here, I was like taking these points and I was like, here it's around -1, right? Here it's around 0. Here's around 1. So what we can do with instantaneous rate of change is not exactly, but almost like down to like small decimal points, we can find the instantaneous rate of change of a point. So let me solve this question with you guys. What is the instantaneous rate of change at the point 2 comma 4? So follow along with me and I'll teach you guys how to solve this question. So the first step you want to do when you're finding instantaneous rate of change is they give you the function, right? So now, and they give you the point 2 comma 4. So let's choose an x value really close to 2. So it's got to be really close, right? Because we're trying to find the closest value and then we plug in our rate of change formula. So a really close value that I chose or would choose is, so if I look back, 2.001. So that's really close to x, right? And now we have to plug in our rate of change formula. But what's one thing we're missing? We have the x value of our second point, and we have the x value of our first point. We have the y value of our first point, but we don't have the y value of our second point. Now, how do we find that? So if we're trying to find the y value for 2.001, they gave us the function, right? Y equals x squared. So we just plug our x value 2.001 into this equation. So 2.001 squared, that just do the calculation for you, 4.004. Now we have our 2 points, and now we're just using our average rate of change formula, right? So let's look at our y value at our second point, 4.004 minus our y value at our first point, which is just 4, divided by 2.001 minus 2. Hope y'all understand how that worked. It was just the average rate of change. And then if we solve for it, we get 0.001 divided by, no, sorry, 0.004 divided by 0.001. And therefore, our average rate of change on at the point 2 comma 4 is 4. Now, this is in this case, it's actually the exact answer, but in many other cases, you guys won't be able to find like the exact decimal answer down to the decimal point, and that'll require some calculus, which you'll learn in calculus. But this is a way to find like approximately the instantaneous rate of change of a point, and it will be tested on in pre-cal. So now I want you guys to take some time to do this question right here. So I hope you guys either have a graphing calculator or you can pull up Desmos on desmos.com. And I'll actually put that in the chat right now. Yeah, that's the website, and you can find the instantaneous rate of change at x equals 2 on this graph. And when you guys get your answer, just text me in the chat. All right, so the Zoom ended early there, so I'm back though. So here's how we solve this question. So yeah, pause it if you're still trying to solve it, but I'm about to do the solution. Three, two, one. Okay, so we know that for instantaneous rate of change, we just take a point really close to the point we're looking for, and then we have to use the average rate of change formula. So what's the average rate of change formula? Over the interval x1, which is our first point, and x2, the average rate of change is y2. This is just our slope formula, right? Y2 minus y1 over x2 minus x1. Okay, so that's simple. Now let's pick our x point. So they gave us 2, so I'm going to pick a point close to 2. So really close to 2. So 2, and then I'll pick 2.001. Oh yeah, that's pretty close. Oh yeah, now we need to find our y values. Okay, well, first let's put down what we know. We know that x values are 2.001. 0, 0, 1, which is our second x value, and 2, which is our first. Okay, now how do we find the y values? So it's actually pretty simple. So since we have 2 as our first x value, we just plug it into the equation to find where our y value is that corresponds with 2. So 2, 4 minus 24 plus 5, that's just going to be negative 15. So negative, sorry. I made a mistake there. It's actually 4 minus 12 plus 5, which is just negative 3. So negative 3, because x squared, 2 squared minus 6 times 2 plus 5. So 4 minus 12 plus 5, which is negative 3. And then we have 2.001. So 2.001 squared is 4.004. So 4.004 minus 12.006 plus 5, which is minus 3. Wait, I should have put that point first. So negative 3.002 minus negative 3, which is just plus 3. So now we do our just our addition subtraction, which is negative 0.002 over 0.001. So our instantaneous rate of change is just going to be negative 2. Okay, now we're moving on to the last lesson on this, which is just going to be our rate of change in linear and quadratics. Okay, so first let's look at this. What type of graph is this? So we got to find that out, right? And how we do that is using this method where we calculate differences and then looking at if it's the first difference, second difference, or third difference, we can determine if it's linear, quadratic, cubic, and etc. So here you might just look at this graph and right away be able to tell, yeah, it's quite linear, but let's look at how we actually do that. So in more difficult graphs, you'll be able to find out. So first thing we have to look for on the x values have to be corresponding. So like -2, -1, 0, 1, 2. So they have to increase like over equal length intervals. So for example, it can't be -2, 0, 1, 3. Like then it's inconsistent, right? So x values are checked. So we'll put check. Then the y values are going +1, +1, +1, +1. So what I said earlier might have like confused you guys for a second, but now it's like it looks pretty simple, right? The difference is this is the first difference of all of them, right? And the first difference is completely the same, which means this can be classified as since it's the first difference, it's degree of 1, which is x to the 1, which is just x, and therefore this is a linear graph. Okay, now let's look at this. So this one, okay, the x is -2, -1, 0, 1, 2. Okay, it checks out. Then let's look at the differences. -4, 2, 8, 14. Okay, our first differences aren't the same, so it's not going to be linear. It's our first difference, so we'll mark it as first. Then our second difference is so the way to find our differences is just this number subtracted by the previous number. So 2 minus -4, same as 2 plus 4, which is 6. 8 minus 2, 6. 14 minus 8, 6. So our second difference, we can clearly tell, are all the same. Second, so this is going to be a polynomial of degree 2, which is x to the 2, which is x squared, which is a quadratic. Quadratic. Now, let's move down. Okay. Now, here's a challenge problem for you guys. So, looking at this table, can you find what degree this graph is going to be? And I'll give you, and you guys can pause the video and find the solution, try to find the solution. And I'll be solving it in 5, 4, 3, 2, 1. Okay, so x values -4, -3, -2, -1, 0, 1, 2, 3, 4. Okay, they're increasing consistently. So we could check off the x values. Check. Now let's look at the y values. Okay. Differences. So first, let's look at 88 minus 263. That's -175. So that's our first difference. And then 23 minus 88, that's just going to be 65. So -65. And then 23 minus 8, -15. 7 minus 8, -1. And then it increases, it's the same. So 1, 15, 65, 175. Okay. So our first difference is not looking good. First difference. And then now let's go to our second column. So this is our second difference. So negative 65 minus negative 175. So it's 110. So it's going up by 110. Then here, negative 15 minus negative 65. So it's going up by 50. Here it's 14. Here it's going down. 1 minus negative 1. No, it's not going down. Sorry, it's still going up. 2. 1 minus negative 1, 2. 15 minus 1, 14. Here, 65 minus 15. That's just going to be 40. No, 50. Sorry. And then back 110. Okay, so our second difference not either. So this is greater than quadratic. So now let's keep going. Negative 60. All right, this is our third column. So third difference, negative 60. And then 14 minus 54. So negative 36. Negative 12. And then it's positive 12. Okay. And then 36. And then 60. Okay, this looks like if we were just looking at this, it would look like a quadratic. So this is signaling me that in the next degree, we're probably going to find an equal difference. So negative 36 minus negative 60, it's 24. Negative 12 minus negative 36, also 24. 12 minus negative 12, 24. And then it just keeps going, 24. So this is actually a polynomial of the degree, the fourth degree, so x to the 4, which is actually called a quartic function. Okay, so that problem was interesting. Now you can kind of see like why we have to use the difference method and we can't always just see right away. And like, and here's another example that would give you a good idea of why. So here and like why it works, right? So 1, 2, 3 is our x, and just have our y all be 2. So here we don't even have to look at our first difference. This is the zero difference. Like there's no difference, right? So therefore the degree of it is 0. And that's why the graph of this would just be y equals 2. So it's another function for like this method that we use. Okay, now let's look at this. So it's okay. Yeah. So the vertex, right? Now we're going to look at the vertex. So vertex is basically the point that where the rate of change is 0 on a quadratic function. Or if you look at like a more complicated function, it's also like where the rate of change is 0. But it has to be a polynomial either degree 2 or greater. So there's no vertex on a linear function. Okay. So let's look at this side, right? Let's do the same method we did earlier. Negative 1. Here it's 1, 1. And here it's going to be 0. And earlier at the start of the video, when we talked about concavity, I mentioned that the vertex is going to be what's it called? Not included where the graph is increasing or decreasing because the rate of change is the vertex is non-existent, right? It's just 0. So if I ask you where this graph is decreasing, you would say negative infinity, parentheses, to 0. And parentheses, because parentheses indicates that it's not included. Brackets. If you wrote this on your test and your question was, where's this graph decreasing? You would probably get points off because it includes 0 and 0 is not included on this. Okay, now let's look at an example question combining these upper two topics. Okay, so what is the graph type? Is the graph concave up or concave down? And where is the vertex on this graph? Okay, so these are questions that I want y'all to answer. And I'll give you, you guys can go ahead and pause the video. I'm going to explain it in three, two, one. Okay, to find the graph type, let's first find the graph type, right? So let's do our difference method. 7, 5, 3, 1, -1, -3, -5, -7. I think I'm noticing a pattern here. As you can see, now the differences are just -2, -2. And this is our first difference. And here's -2, -2, and so on, right? We get the point here. The second differences are all the same. So this is a quadratic. I'm just gonna write quad for time's sake. And then if we like sketch out this graph, right? By the way, you can really tell if you look at it. So first it's increasing by uh first, the graph is increasing by 7, then 5, then 3, then 1, then -1. So the rate of change of the graph is decreasing, right? It's increasing less as we go on. So like 7, 5, 3. So that shows that, right? But if we just sketch out the graph, when x is 1, y is 0, x is 9, y is also 0. And then let's look at x is 5, y is 16. So just imagine this point is 5 comma 16. You can tell that the graph looks something like this. And this looks like our usual frown face and where the rate of change is decreasing. So therefore, it is concave down. Now let's look at the vertex. So how we find the vertex off a table or even off a graph is when we have two of the same y values on a quadratic function, the vertex is always going to be the midpoint of these two values. So for example, 0, 0. Okay, these are two same y values. So what's the midpoint of this? And the midpoint formula is going to be just the second one minus the first one divided by 2. So 9 minus, I mean, sorry, it's the second one plus the first one divided by 2. So 9 plus 1 divided by 2, 5. So that's going to be our midpoint. So 5, comma 16 is going to be our vertex. Now, this is one last challenge problem for you guys, and you don't have to do it, but this is something that could be asked as an extension question on a test, and it's going to be the last problem of the video. Okay, Tim is playing catch. He throws the ball from a height of 5 feet when the time is 0 seconds. Then the ball reaches its maximum height of 50 feet when the time is 7 seconds. Then the ball rolls down a hill which led to a ramp. The lowest point of the hill was 30 feet deep. The ball reached a height of 10 feet after rolling up the ramp. Then it finally hit the ground in 20 seconds total. So the question is, how many points of inflection would there be on a graph which represents the height of the ball over the 20 seconds? So the height of the ball over the time. So now I'll give you guys can pause the video and try to answer the question, and I'm gonna explain it in three, two, one. Okay. So here we go. Now, our y-axis is our time. Not our time, sorry, our height. So we'll label it as h, and our x-axis is our time. So just t for time, or just write out time. Time, right? So let's get our points we have. 0 seconds, it's 5 feet. So 5 when it's 0 seconds. Okay. Then it reaches a maximum height at 50 feet when the time is 7 seconds. So time is 7. Also, by the way, the maximum height, that indicates that that's one of the vertexes of this graph because the maximums and minimums, those are going to be your vertexes. It's a neat trick to use for later. And then there we go. Maximum height is 50 feet. And then our next point that we have is the lowest point of the hill was 30 feet deep. It rolled down a hill, which led to a ramp. So somewhere here, it rolled down all the way to -30 because the hill's 30 feet deep. And it rolled, we'll just say like here, right? And then finally, the ball, let's extend this by the way. Okay, then the ball reached a height of 10 feet. So it is as 10. It's not proportionate, but it's not perfect, but it'll do. And then finally, it reaches the ground at time equals 20 seconds. So let's draw out this graph. So it goes something like this, all the way down and up, then down. Okay, Now, I think most of you are starting to see how much points of inflection there are. So it's going to be, if we look, first, we look at the graph, it's making that frown face, right? So this indicates that the start of the graph is concave down. So it's going up, the rate of change is decreasing, so decreasing, decreasing, decreasing. And somewhere around here, I'm just gonna say like here, right? It doesn't have to be the exact point. This is one point of inflection, we'll say, around that area, right? Because the rate of change is decreasing, and all of a sudden it starts increasing, and because it's going up, and then it's making that smiley face, which indicates that it's concave up. And then it's making this frown face again. So it tells me that it's going from concave up to concave down somewhere there. So, and we can see it's increasing. And around here, right, is going to be another point of inflection where it changes from concave up to concave down. So in total, there's going to be one and two. 2 points of inflection is our answer. And one thing you may have noticed is the number of times it's concave up or concave down. So here it's concave down 2 times and concave one time. So a total of 3 different like places where it changes concavity. I mean, not changes concavity, but 3 different areas on the graph with different concavities. So therefore, the inflection points is one less than that. So it's two. So yeah, two, and that's just going to be our answer. And just another thing you can notice is like 7 comma 50. This is one vertex, V for vertex. And then here we don't know the time, but -30, that's another vertex. And that's going to be it for the video. And if you guys did find this useful or helpful, I would really appreciate a like and a subscribe because I put a lot of time and effort into this and I don't get paid for this. So with that being said, I hope you guys have a great rest of your day and I'll see you guys later.